Okay, the sketch of the proof for integral test. Suppose that fx be a continuous function and fn equals to a sub n, the n term. So basically, this makes it fx is the continuous superposition function of a sub n. Now, and suppose that the function is non-negative and decreasing. Actually, we just need them to be eventually non-negative and eventually decreasing. Then we have that the sum, the series, and for n, I'm sorry, it should be 1 here. The series from 1 and the integral from 1 of the function should be both convergent or both divergent. Now, if we try to sketch the graph of the series in figure 5 and 6, I take these pictures from the book. Now notice that if I kind of like arrange the block a sub 1, the first term is the block which is at 1 to the right of 1. Okay, now notice that the sum of this, the area of these blocks here, will be more than the integral. Will be more than the integral that we have here. This integral of this curve. You see, we have extra here, right? You see that? So the sum, the infinite sum of that series, the series will be greater than the integral from 1 to infinity. The series from 1 to infinity will be greater than the integral from 1 to infinity. Now, on the other hand, when we observe the first graph, notice that figure 5 there, notice that if we start from that 1 here, so if this is x, when x equals to 1 is here, okay, and then I start the second term, instead I draw it backward, okay, the second term, okay, the third term, but I draw it backward, okay, instead of forward like figure 6. Notice that all these boxes here will be below the curve fx, right? Such that the integral of this curve, starting from 1 to infinity, will be greater than the sum of the area you get under these boxes. Okay, now therefore we get this inequality here. The series starting from the second term, not the first term. The series from the second term is less than equals to the integral from the first term. Now, and then when I play with the inequality, both of these inequality here, then this infinite series from 1 to infinity is bounded below by this blue part here, right? It's bounded below by this blue part. Okay, but this infinite series here is actually the first term plus the series from the second term, right? They are equal. But at the same time, in the top inequality here, okay, the second term is this guy here, is less than the integral from 1 to infinity. Okay, so the whole thing, the whole thing here must be less than equals to the first term plus that integral. Now then, what can we say from here? Well, notice that then the series, if the series is convergent, okay, it implies the integral over convergence. That's also convergent. Why? Because the blue part here is positive but less than this guy, right? Now, likewise, if the integral is convergent, which means this is convergent, okay? Now, plus sum up constant, the first term is a constant, then it is an upper bound of that integral. Now, what happened then? If the integral is convergent, therefore the series also convergent. Okay, now what happened if one of them divergent? Then all three of them will be divergent. Okay, now that's the sketch of the proof. Now, what I want to go on with is, how about the error estimate? Let me first define my infinite sum as the summation for the first n terms, which we usually call S sub n, and the remaining term. And then the remaining term after you add the first n terms. Now, from the picture on the left-hand side, we see, now suppose up to here we get the sum up to the n term. Okay, the sum up to the n term. Notice that the next term, the n plus first term, n plus second term, is always below the area is less than the area of the integral. Do you see that? Okay, so what happened is the following. Then the first n terms, okay, now the remaining terms from n equals 1 to infinity is bounded above by this integral here. It's bounded above by that integral. But at the same time, we also see that the same expression we have up there. Okay, now the sum from the n plus first term is actually is greater than the integral from n plus 1. Okay, notice that the summation, the sum of the area of the blocks here, always greater than by this much, by that much, right? Okay, if is greater than, so the summation, the series, the remaining series is greater than the integral from n plus 1. Okay, now the same play that we have up here, then notice that the infinite sum, give me a second, let me delete those highlights. Now then you see that the infinite sum therefore is bounded above by the nth partial sum plus the integral from n. bounded below, but the nth partial sum plus the integral from n plus 1. Okay. So then I basically try to answer this question. So we try to answer this question. If we add, if we get Sn, that's the sum of the nth partial sum. Okay, if we get Sn, then what is the upper and lower bound of the error? Now, this expression here answers our question. Okay, that expression answers our question. Now, upper bound and lower bound helps us to anticipate what is the maximum size of wrong error. Okay, now let's apply this formula or this idea here to one example we have. I will pick example number 39. Hold on, give me a second. Try to delete. I get example from number 39 here. The question is to estimate this series, this infinite series, up to correct to 5 decimal places. Correct to 5 decimal places. So it means my error is at most 0.00001. Okay. In other words, then how many terms should we add such that the error, how many terms we need to add, what is the K, how many terms we need to add such that the error, which is represented by this integral here, is less than 0.00001. Okay, I did my integration and I found that the K has to be at least 4.5. The K has to be at least 4.5. So I use K equals to 5. Okay, so I use K equals to 5. Now, we will do this kind of computation later on again, which I believe I did last time, but I didn't do it organizedly, well organized. So this time, I try to do it in more organized fashion. Now, so basically, we try to find the infinite sum of this sequence, so this infinite series here, okay, and approximate that using the fifth partial sum only. Now, according to our computation earlier, when I add the first 5 sums, the first 5 terms, the sum that I get, okay, the sum that I get here, let me use another color. So this guy, which we call the fifth partial sum, okay, this sum here is of less than 0.00001 from the actual sum if we add them up to infinity. Okay, so if you want to be accurate to 5 decimal places in this case, then I just need to add the first 5 terms. Okay, What happened with the rest of the terms, Thomas? The 6th, the 7th, the 8th terms? Of course, it will change the sum, but the change is so small such that if you round it to 5 decimal places, there's no need for you to add that far. Okay? Now, here's the thing though. I tried to picture this using Excel. Let me direct your attention to my Excel worksheet here. Now, I use Excel to show you the computation. Now, here, this is my term. This is my term n. This is the nth term. This is my 2n plus 1. Okay, so this is my first term. Okay, so 2n plus 1 looks like this. Then if I take it to the power of -6, that's what it looks like. Okay, and then the second term, 2n plus 1 is 5. Then 1 over 5 to the 6. 1 over 5 to the 6 is this. Now, the one I have on the right here, this is the nth partial sum. Basically, S2 means, like, S2 means the previous sum up to plus the current term. Okay, S3 will be the sum of the first 3 terms is basically the sum up to the second term plus the third term. Okay, so basically this is the end sum. Now, according to our computation earlier, we can stop up to the 5th term. Now, notice that at the 5th term, the decimal place will be, the decimal will be 0.00145, right? 0.00145. Now notice that even if I go on further and further and further, if I continue my computation, notice that there's no change. There's no change for the sum. Like if I look at if I add up to the 24th term, the sum is still 0.00145 if I round it to 5 decimal places, right? You see what I mean? Okay, now you can go on further. I can go on further here. And you will see there's no significant change on the sum. Oops. Yeah, there's no significant change on the sum. Unless, I mean, you need to decide how many decimal places you want to go, right? But let me increase the decimal places. You see, it doesn't change up to the 10th decimal place starting from the 26th term. Okay, that's 10 decimal places. If you want to be accurate to 5 decimal places, you only need to go to 5 terms. Okay, in fact, we get the same 5th decimal place even at the 4th term. If we stop at the 4th term, then we will get the same 5th decimal place compared to if I go to 5th decimal, if I go to the 5th term. Okay, but we are guaranteed that if we go to the 5th term, then it will be accurate to the 5th decimal places in this case. Okay, now that's an illustration of what we did earlier with our in our notes. Okay, now that's how I try to explain that error estimate. Now let's go on further. Let's do one more question. Suppose, I think last time I did number 38, huh? Last time I did number 38. How about number 40? So number 40, for example, we have how many terms of the series, the summation n equals to 2 to infinity of 1 over n times ln n squared will we add to find its sum, to find its sum to within 0.01. In other words, we just need 2 decimal places accuracy. Okay, so we need to find k such that the integral from k to infinity of 1 over x ln x squared dx is less than equals to 0.01. So let's start doing that now. So that's equals to limit t goes to infinity, integral from k to t 1 over x ln dx. What kind of substitution you want to do? Because I missed the square, by the way. Sorry. I think I will use the substitution u equals to ln x such that du equals to 1 over x dx. Right? So the integral will be, this is ln k, this is ln t. Okay, and then we get u to the power of negative 2 du, which if I go on further, this is limit t goes to infinity of, what is the integral of that? That's negative 1 over u. That's right. From ln k to ln t. So that's equals to 1 over ln k minus limit t goes to infinity of 1 over t. But that's 0. So this is 1 over ln k. Now the thing is, we need this to be less than equals to 0.01. Is it right? Okay. So 1 over 0.01 should be less than equals to ln k. Or ln k should be more than 100. So k has to be greater than e to the 100. Wow, that's a very big number. It's a very, very big number. So, yeah, that's a very, very big number. So basically, we need to add up to the ceiling of, if you round up, of e to the 100. Okay, and basically we need to round it up to the next integer. Okay, let's call this k. Let's call this k. So it's basically we need to add up to that k 1 over n ln n squared going to add up to k such that this sum here is approximately equal to the infinite sum. Okay, with error, with error, with error less than 0.01. That's a lot of terms to add, but at least we don't need to add up to infinity, right? I wonder how big is e to the 100. I don't have my calculator here. Let me go back to my...
It's 2.7 times 10 to the 43.
Ooh, that's way too big. Wow, 10 to the 43. Okay, well, that's a big numbers to add. a lot of numbers to add. But at least we know that by integral test, we know that this is actually convergent, right? This series is convergent. Okay, we know that eventually the series, the number, the value will increase less and less significant. Okay, I'm honestly surprised with this number though. I'm honestly surprised with this such a big K that I need to get. Yeah, that's a very big K. But if you take a look on number 41, if you take a look on number 41, you will see that it is possible. In fact, for number 41, for you to have error less than that, then we need to add more than 10 to the 11,000 something terms. Yeah, it's quite a lot of terms to add to have such kind of accuracy. Okay. Oh, by the way, I have to say the following though. Now, it doesn't mean we have to add up to this many terms to be at that accuracy. No, in general, that's not the case. It is just saying that if you want to be guaranteed that the error to be less than 0.01, then to be guaranteed, then you will add that much. It is possible, that many terms, but it is possible before you reach that number of terms, you already reach that accuracy. It is possible. Okay, as you've seen in my earlier Excel earlier, right? According to our computation, at the 5th decimal place, our accuracy will be up to 5 decimal place, right? Okay. Now it is guaranteed. Now apparently, according to our summation here, visual summation here, you see that even if we add up to 4 terms, we already reach that accuracy. If you round it to 5 decimal places, maybe I do that setting here. So maybe 5 decimal place. Okay, so I do this to this number, comma 5 decimal place. Copy that. You see, like at the 4th decimal place, we already reached that accuracy. Okay, even though our computation says that you need 5 terms. You need 5 terms to guarantee that accuracy. Okay, but it is possible that if by then you already reach 5th decimal place accuracy. Okay, that's what I'm saying in our my explanation earlier here. Okay, now that's for 11.3b. Let me go on to 11.4. In this 11.4, we will have a comparison test. 11.4 comparison test. There are actually two comparison tests. The first comparison test, the comparison test. Suppose that we have two series. So suppose we start with, suppose the series A sub n and B sub n are series with positive terms. In other words, A sub I and B sub I are positive. Okay? Then if series B is convergent and the term by term comparison B is greater, then series A is convergent. If you bound it above by if the series A sub n, if the series A sub n is bounded above by the series B sub n. Now it's already positive, right? It's already positive terms. So of course the summation here is greater or equals to 0. That's one. Second, it's also increasing. Notice that S sub n is actually an increasing term, increasing series, increasing sequence. S1 compared to S1 plus S2, I'm sorry, compared to S2, compared to S3, compared to S4. It is increasing because from S1 to S2, you need to add a positive term. From S2 to S3, you need to add positive terms. You need to add positive terms, right? Okay, so because you keep on adding positive terms, then the sequence Sn, the nth partial sum, is increasing. Now, at the same time, it is that it is bounded above. At the same time, it is bounded above. Okay, so let me say it this way, that as the nth partial sum is non-negative and it is increasing, right, and bounded above. Right, by monotonic bounded theorem, this Sn must be convergent. Okay, that's the idea. So if I can bound it above by something convergent, that series is convergent. And if I bound it below by something divergent, if the series A sub n is divergent. To be more precise, divergent to infinity. And but term by term comparison, A sub n is lower or smaller than Bn, then the series Bn is divergent. Okay, now the idea is similar to what we have earlier. Suppose this guy here is infinity, then the summation of the terms greater than a sub n must also even greater. Okay. Now, how do we use this? Well, basically, you may see a series that is you can just solve it by comparison. If you remember this one of the questions that I did before, I don't remember precisely, but let's see. Let's see. Oh, do you remember this one? The summation of from 1 to infinity of 1 over n times n plus 1. Do you remember this one? That we did this is done in section 11.2 by telescope. Actually, can also be done by integral tests. But for us to do that integral test, we need to do partial fraction decomposition, partial fraction decomposition in between. Okay, now I will show you another way. Now I will show you that this problem can also be done another way. What is that? What is that? Notice that note that 1 over n times n plus 1 is less than equals to 1 over n squared. Is it right? Well, that's because n is less than equals to n plus 1 as long as n is positive. And then if I multiply both sides by n, I get n times n plus 1. And therefore the reciprocal we change for the reciprocal which refers the inequalities. Right? Okay, so that's the proof. Now, therefore, so the sum of this series, the original series that we try to add, must be less than equals to the series of 1 over n squared. Right? Okay, now don't forget that these terms are also non-negative. Okay, but the sum of 1 over n squared is convergent by P-series, right? Where the P is equal to 2, which is greater than 1. Then this series n equals to 1 to infinity of 1 over n times n plus 1 is convergent by comparison theorem, by comparison test. Okay. Now let's try to do some problem from our textbook. For example, I don't know what number. I don't know what number. let's say number 10. Why not? Let's say number 10. Number 10, the summation from k equals to 1 to infinity of k sine squared k over 1 plus k cubed. Now notice that, so the solution, notice that k sine squared k over 1 plus k cubed, this is less than equals to k over 1 plus k cubed, is it right? Of course, I need to say for k greater equals to 1. And we start from 1, that's why I say that. Okay. But I also know that this term here is less than equals to 1 over 1 k over k cubed. Is it right? Which I can simplify to be 1 over k squared. Now notice that these terms are all positive, non-negative at least, okay, and bounded above by 1 over k squared. So basically the sum from k equals to 1 to infinity of k sine squared k over 1 plus k cubed, this must be less than equals to the sum, the series of 1 over k squared. By p series, p equals to 2, which is greater than 1, this series on the right end of the inequality is convergent. And by comparison theorem, or by comparison test, the series that's so ugly is also convergent. Now, let me show you a situation where we still can apply that. And in fact, I believe we did this problem before. The summation of 1 over n squared plus 4 from n equals to 1 to infinity. I think this was one of the suggested homework I asked you to do, number 17 from 11.3. And of course, we have shown, if you do the problem, and you see that this is convergent by integral test. Okay, it's convergent by integral test. Now, I believe I have shown you a sketch of comparison test. Notice that, so solution, other solution, alternate solution for n greater equals to 1. Notice that n squared is less than equals to n squared plus 4. But of course, this is non-negative, right? Such that 1 over n squared plus 4 will also be non-negative, yet it is less than 1 over n squared, right? Okay, so this series 1 over n squared plus 4 from 1 to infinity is less than equals to the series from 1 to infinity of 1 over n squared. Now, by P series P equals to 2, which is greater than 1, the series from 1 to infinity of 1 over n squared is converging. And then by comparison test, the other series, which is less than and still positive, is still converging. Okay, so we can use integral tests, and now we can use comparison tests. Now, here's the issue. Here's the issue. How about this infinite sum that we use from 3 to infinity of 1 over n squared minus 4? How will we do this? There are actually two ways to do this already. There are two ways to do this. The first one, you can use telescoping sum. Another one, you can use integral tests. Well, both of them requires you to do partial fraction decomposition. Both of them requires you to do partial fraction decomposition. Okay, but we cannot use comparison tests. We cannot use comparison tests. Why? Because n squared minus 4 is less than equals to n squared. Yeah, it is still positive. It is still positive for n greater or equals to 3, right? But it's less than such that when I do the reciprocal, then 1 over n squared minus 4 is still greater than, not less than. It's greater than. You see? Okay, so the thing is, I know that this guy here, the sum, the series for this is convergent. But if you bound something by, you bound a series below by something convergent, doesn't imply this is convergent. Okay, so this guy is convergent, right? But it doesn't mean this guy is convergent. Why? Because you bound it below by something convergent. No, you cannot, right? You cannot. Notice that in our sketch of proof earlier, we require that for you to be convergent, it has to be bounded above by something convergent, not by something below that is convergent. Okay, it has to be bounded above by something convergent because we want to use the monotonic bounded theorem. Okay, now monotonic bounded theorem does not apply for a series that is not bounded. Remember? Okay, for a sequence that is not bounded. So coming back here, you see that comparison test doesn't work. However, we know that n squared minus 1 over n squared minus 4 will behave quite similarly with 1 over n squared when n is very big. When n is very, very big, much, much larger than 0. Okay, so they behave similarly, even though 1 over n squared minus 4 is greater than, okay, but when n is very big, they behave similarly. So can we then say that this series, 1 over n squared minus 4 to be convergent or divergent using the fact that when n is very large, they behave similarly. Then I will need to introduce you with another tool, also based on on comparison test, called the limit comparison test. What limit comparison test says? Suppose the series A and the series B are series with positive terms. In other words, A sub I and B sub I are non-negative. Okay, and the limit as n goes to infinity of A sub n over B sub n is constant C, where C is a finite number. Finite positive. Well, it will be positive because the terms are positive. Okay, finite positive. Then, oh, yeah, it has to be positive. Maybe I say that it has to be greater than 0, not equals to 0. Not equals to 0. It has to be strictly positive. Okay, then the series A sub n and the series B sub n are both convergent or both divergent. Okay, now how do I use this? Going back to the question that we have earlier, for example, the series 1 over n squared minus 4. I said earlier that this series is actually convergent. Okay, you can use telescoping sum, you can use integral test, but I want to show you how we use limit comparison test. Note that n squared minus n squared is positive, therefore 1 over n squared is also positive, right? Especially for n greater or equals to 3. Where do you get that 3 from? From here. Okay, and in reality, you don't have to start from 3. You can start from 10. It's fine, because what we need is eventually positive. Okay, it's eventually positive. Now, then I will do this. Limit n goes to infinity of 1 over n squared. The series, the terms whose series I know to be convergent. Note that this series from 3 to infinity of 1 over n squared is convergent by p series p equals to 2, which is greater than 1. Okay, now then I do the limit comparison test with that 1 over n squared minus 4. This is equals to limit n goes to infinity of n squared minus 4 over n squared. By the way, can I use L'Hopital rule here? The answer is no, you cannot use L'Hopital rule for this limit. The reason is The n here are integers, they are not continuous. Okay, so no, you cannot. But what we can do is we divide the top and the bottom by n squared.
Professor,
Uh-huh.
isn't it the sum of a sub n over b sub n? So it'd be 1 over n squared minus 4 over 1 over n squared?
I can just do either one.
Oh, okay.
Yeah, because as long as the limit is positive finite.
Okay.
Right? Okay. So the way you see is this is the series that you try to prove, and you use this series. But with the condition we have here, it can be either one. Because both of them will be convergent or both of them will be divergent. So as long as you know the convergency of one of these series, then the other series will follow. Right? So coming back to that, what I did here, you can use either one. You can use either one. You can use 1 over n squared minus 4 on the top.
Okay, thank you.
So this is n squared over n squared. So this is limit n goes to infinity of 1 minus 4 over n squared over 1. This is equals to 1, which is positive and finite. Okay, so by limit comparison test, this series n equals to 3 to infinity of 1 over n squared minus 4 is convergent. Yeah, but before you say that the series that you try to prove is convergent, you need to come up with another series and show that this series, I'm talking about this series here, I use this series for my limit comparison test, but you need to first state that it is something that you know to be convergent or know to be divergent. Okay. Now let's go on. Let's go on. We go back to our examples, problems. Would you like to pick some questions from page 450, 750? Page 750.
I'm barely getting the book out, so give me a few seconds.
Sure. Oh, number 18. Let me go for number 18. Number 18. The summation of 1 over from 1 to infinity of 1 over 2n plus 3. Notice that the degree at the bottom is 1, so you can actually compare this with 1 over n. Okay, solution. Consider harmonic series, the harmonic series known to be divergent. And then I do limit comparison test. And to infinity of 1 over 2n plus 3 over n. That's limit n over 2n plus 3. Fast forward, what will this be?
Is it 1/2?
Okay, so by limit comparison test, the original series that we try to see if convergent to be divergent, that must be divergent.
Professor, do you also always want us to state that all the terms will be positive for n is greater than or equal to 1?
Supposed to. Yeah, we're
Okay.
supposed to say that.
Okay.
Yeah. Mhm. But we are supposed to. So what am I missing here? My harmonic series is already known to be all positive. Well, anyway, that's one example. Let's list first what we have learned, the tools that we have. First one, we have geometric series. Geometric series says that if R between -1 to 1, it's convergent, right? Second, we have divergence test. That says that if A sub n is not convergent to 0, then the series is divergent. Okay, and the third one, what else? Integral test. Oh, we have what's that, telescoping sum. We have integral test. And then we have comparison test. And then we also have limit comparison test. Okay, we have more tests coming though. We have more tests coming to see if it is convergent or divergent. Now, I can actually do more things here. Another solution, alternate solution. Notice that this sum from 1 to infinity of 1 over 2n plus 3 is equal to 1 over 5 plus 1 over 7, that's the second term, right, plus the sum from the third term and on. Is it right? But this guy here is greater than, this guy is here is greater than 1 over 5 plus 1 over 7 plus the series from 3 to infinity of 1 over 2n plus n. So I replace that 3 here by n. Because I divide by something greater than 3, because my n start from 3 here, right? Okay, 3 and on. So this is 1 over 2n plus 3, 1 over 2n plus 4, 1 over 2n plus 5, and definitely this guy is greater than this guy. But you notice that this is the summation from 3 to infinity of 1 over 3n, and I can factor that 1/3 out, right? I can factor that 1/3 out. Then you say since that n equals to 3 to infinity of 1 over n is divergent by harmonic series. Okay. Then the greater series is divergent by comparison tests. So I didn't use limit comparison tests, I used comparison tests. Okay. Apparently, the limit comparison test is a lot shorter, right? Can you choose more questions?
Could we do number 30?
30. Ooh. Number 30. The series from 1 to infinity of n factorial over n to the n. You saw this question before, I believe. I think you saw this one in your last test. Remember that? Well, anyway, don't worry about it. Okay, so show that it is convergent or divergent. Any idea? Let's write this first. N factorial over n to the n is 1 times 2 times 3 times 4 all the way to n over n times n times n times n all the way to n. Is that right? And notice that all of these terms here, this term here is less than 1. This term is actually, all of these terms is actually less than 1, at most equals to 1. All of these are at most equals to 1, 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 at most equals to 1. You see that? Such that I can say this is bounded above by 2 over n squared. If I only see the first two terms. You can make it 6 over n cubed. You can make it 12 over n to the 4th. You can. It's okay. You know, but the idea is I want to bound it above by a series. I want to bound it above by a series that I know will be convergent. Right? Okay, I know I bound it above by a series that is convergent. Now you may wonder, Thomas, then why don't we just use 1 over n? Now the thing is, the series 1 over n is divergent. Okay? And if you bound it above by something divergent, it doesn't say anything by any function or any series below that. Okay, so this, if you do it only the first term, it doesn't work. Okay, but if you start with the 2 of them, it will be good. Oh, good. Okay, you can use, again, you can use 6 over n cubed. Okay, now then, let me go on. This, where's my pointer? This n factorial over n to the n is surely positive and less than equals to 2 over n squared. So this series n factorial over n to the n is less than equals to the series 2 over n squared. Which we know equals to 2 times the series 1 over n squared, which is convergent by p series p equals to 2. The series, this series is convergent. So, by comparison test, this series also convergent. Okay. That's for, I think we are good with that, huh? Don't you think so? Oh, you know what? How about question number 32? I really don't know the answer here. Number 32. The series from 1 to infinity of 1 over n to the 1 plus 1 over n. Honestly, I don't see this anymore. Like, is it convergent or divergent? How to approach that? I have no clue. Any idea?
Give me 1 second. Let me see. I want to say we could use the P series, but I don't know.
The thing is, when you try to use P series, it doesn't really follow P series though. You know, the P series is like n to the P, right? And the breakdown will be, the cutoff will be its convergent if P is greater than 1, divergent if P is less than 1, less than equals to 1. Now the thing is, when we look at the limiting here, this guy here, the limiting is actually 1. So when n gets really, really big, this behaves like 1 over n.
Ah, okay, thank you.
Yeah, it will behave like 1 over n. I really don't know how to do this one. I really, really don't know how to do this. Let's do limit comparison test. So this is my scratch work. I still question, okay, still question mark. So I will compare this guy here, compare that with, compare to 1 over n, okay? So 1 over n, big over 1 over n to the 1 plus 1 over n. This is n to the 1 plus 1 over n over n, which will be n to the 1 over n. under limit condition. So how do we do this? So this is what we need, right? N goes to infinity, right? That's what we need. Limit N goes to infinity. Limit N to infinity. So let y equals to x to the 1 over x. So natural log of y equals to 1 over x natural log of x is right. So I apply limit x goes to infinity of ln y equals to limit x goes to infinity of ln x over x. Oh, do you start seeing some light at the end of the tunnel? Then I can apply L'Hopital rule. And that's the reason I need to use this superposition continuous function. Okay, and I get this is 1 over x over 1, which goes to 0. On the left hand side, I get natural log of limit x goes to infinity of y. Okay, so limit x goes to infinity of y is equals to e to the 0, which is 1. That's a positive number, right? Okay, so limit n goes to infinity of n to the 1 over n is equal to 1. Okay, so by limit comparison test, the series 1 over n to the 1 plus 1 over n
diverges.
Repeat again?
I just said diverges.
Yeah, it diverges because and I try to be more clear when so that we don't lose track of what we have been are both diverges. Does it make sense? Okay.
Yeah, so for full credit, we are writing all of that out, including repeating the series so we know what we're talking about for full credit on the exam.
Yeah, because we have two series that we are dealing with here. That's the thing. So just say the series. Just say the series. It's not clear which series you are talking about.
Okay.
Right.
Sure.
Mm-hmm. Okay, so at least it seems like okay. That's my scratch paper, by the way. Let's make it nicer. Let's make it nicer. Here's my pointer. Okay. So I will say consider the harmonic series known to be divergent. So then I limit n goes to infinity. So I will do copy paste of this. I will do copy paste of this thing here. I'll do copy paste of this thing here. Cool. Then equals to 1. So my limit comparison test is series is divergent. Okay. So we spend more time and more work actually on showing the limit to be positive, finite number. But honestly, when I look at that question, I didn't know the answer. I couldn't even tell if it is divergent or convergent. I really have to do some scratch work. Okay. Now let's do so in this section, we have learned two things. We have learned comparison tests and limit comparison tests. Now then, how about estimating? The next topic, a subtopic, how about estimating sum? How about estimating sum? Now suppose I have a series. Suppose I have a series and I know that it is convergent. I know it is convergent. Then suppose we have the kth partial sum. Suppose that we have the kth partial sum for the A series. So the sum n equals to 1 to k of A sub n. Okay, now then how about the error? How about the error? We will do it in the following way. Now, let's say the summation, the actual sum is the summation of the A series up to infinity, which I will break up as the sum from 1 to k plus the sum from k plus first to infinity. Now using this comparison here, using that comparison here, okay, using that comparison there, I will say that this is less than equals to the sum from 1 to k plus the sum from k plus first to infinity of Vn. Okay, so basically what I did is I changed this part here to this. Okay, because the A terms is less than the B terms. Is it okay? Is it okay? Now, therefore, if I rewrite this here, the infinite series, is less than equals to the kth partial sum plus the summation from k plus first to infinity of the b's. Now, then the thing is then the error, which is s minus the nth partial sum of the A series, is bounded above by the remaining terms of the B series. Now, the thing is, we may be computable, evaluated by other method. Okay, let's say for example, we get number 36. Number 36. Use the sum of the first 10 terms to estimate the sum of the series. Estimate the errors. Use S10 to estimate S and find the error, which is the difference between the actual sum, which we hardly know, okay, to the 10th partial sum, which we can compute by adding the first 10 terms. Okay, so let's see, this summation here n equals to 1 to infinity of 1 over 3 to the n plus 4 to the n. Can I say that this is less than equals to the sum from n equals to 1 to infinity of 1 over 3 to the n plus 3 to the n? Can I do that? Yeah, 4 is greater than 3. So 4 to the n, 3 is less than 4, right? So 3 to the n is less than 4 to the n for n greater or equals to 1, right? Okay, and therefore 3 to the n plus 3 to the n will be less than 3 to the n plus 4 to the n. Then I can do the reciprocal. Okay, now the thing is, when you say this, you need to prove it. Okay, you need to show the proof, maybe next to it or below that. Okay, maybe I say claim here. Okay, and that's the proof. Then on the right hand side, I see that I have 2 times 3 to the n on the denominator, which I can pull the 1/2 out. Right? Okay, so apparently you can see that this series is actually convergent. Now the thing is, we need the error up to the 10th term. So the error up to the 10th term, so this should be what here? What number should be here?
10?
To be more precise, 11.
Oh, I see, yeah.
11 because of what we have here. Okay, so the summation up to the 10th term, the sum of the 10th term, the remaining is starting from the 11th term. So what happened here, it will be up to 11th term also, 11th term also here, 11th term also here. Okay, so this is equals to 1/2 times the first term is 3 to the 11 over 1 minus 1/3. So this is 3 to the 12 over. I'm sorry, not 3 to the 11. The first term is not 3 to the 11. This is wrong. It's supposed to be 1 over 3 to the 11. That's the first term, right? I wonder why I get such a big number. The error is supposed to be very small. So I will get 1/2 times 1 over 3 to the 11 times 3 over 2. That's 1 over 4 times 3 to the 10. Okay. So our error will be less than that. No. I wrote it incorrectly. The error should be here. So the error will be less than that. Okay, now with the time I have right now, let's do that experiment. Let's do that experiment. Let's go back to my Excel. Yeah, I use Excel because then you can see term by term. Okay, what happened? And then if this is the first term, then it will be 1 over 3 to that term, to that exponent, plus 4 to that exponent. The summation for the first term basically itself. Now what happens if we have the second term? Then the second term's value will be, oh, okay. And then the sum up to the second term is the previous sum plus the current term. Okay, now the thing is, I will extend this up to the 10th term. So what will the sum be? So that's the sum up to the 10th term. Okay, the sum, that's the sum up to the 10th term. Now, how about the error bound that we have earlier? The error bound that I have earlier is, the error bound I have earlier, error bound was 1 over 4 times 3 to the 10th. Huh? Is it right? Look at your note. That's what I get. Okay, so if I try to write this in decimal, if I try to write that in decimal, it's 0.0000042377. I gotta change it. Basically, we start having. Maybe I use this. I need to use this too. So you see, the change will start at the 6th decimal place. Okay. Now, imagine if I go further with this, go a lot further. Go a lot further. Now I expect my sum here. Will not change. My sum will not change more than 6 decimal place. Okay, so notice that if I rewrite this as decimal, 197,882. This is the 6th decimal place. Okay, this is the 6th decimal place. Okay, now notice that It will not change though. Maybe I put it this way. Let me see. The difference between this guy here from this guy. You see, if I compare to the 26 decimal sum compared to the 10th partial sum, the error here is less than that one. Right? You see, this is the 7th decimal place. This is still the 6th decimal place. Okay. Now, if I want to go even further, let me try to be crazy. Suppose I go up to the 100th term. Maybe no. Up to the 50th term. Oh, there's no more change, huh? You see? The number here, subtract by what I have at the 10th term. Yeah, it still differ by only 3 times 10 to the negative 7. Okay, so if I want to be, when I add the first 10 terms, my error will be less than 5 decimal places difference. Okay, now let me stop here, give us a break. Right now it's 6:08. Let's come back at 6:20. Let's start again. I'm done with 11.4. I wonder if you have any question you would like me to do. If not, then I go on to 11.5. Go on with 11.5. 11.5.
Professor, did you say homework for the 11.4?
Oh, you are right. Let me go back to 11.3. So 11.3, I think I asked you to do a lot of them already, huh? Can you remind me 11.3? How far was the homework?
3 to 31 is what I have written down.
3 to
Yeah, I have that
31. Okay, so for 11.3, for 11.3D, this is just the homework to do. Try number 37. I think you did 39, but you tried to do the thing. And how about number 41? And then for 11.4, suggested homework to do number 3 to number 35. I think that's what we need. And then now 11.5 alternating series. Okay. A series is alternating is called alternating series. If the terms are alternating terms. Okay. Suppose for example, a very well-known one called alternating harmonic series. That is 1 minus 1/2 plus 1/3 minus 1/4 and so on and so forth. If we use the summation notation, that's from 1 to infinity, then I have 1 over n for the harmonic part, and then the alternating -1 to the n is 1. I usually call this the alternator, the one that make it positive, negative, and this is the harmonic part. Okay, now in general, you can see that harmonic series can be written as the summation of -1 to the n plus 1 or n minus 1 of Bn, or the summation of -1 to the n of Bn. Depends on, do you start with positive or negative. So the alternator here can be adjustable. If n equals to 1 and the first term is negative, so you have this one. If n equals to 1 and the first term is positive, then you use this one. You can, of course, also use n minus 1 here instead. Okay? And therefore, the Bn will be the positive term. Okay, as you can see in our what we saw earlier here, this 1 over n is the positive term. 1, 1/2, 1/3, 1/4, right? And the yellow one is the one alternating it. Okay, now alternating series test says the following. Alternating series is convergent if it satisfies this requirement. The first one, the Bn is eventually decreasing. Okay, our textbooks say Bn plus 1 is less than equals to Bn for all n. Okay, so the next term, the next positive term is, so the Bn, the positive terms, the positive part. Okay, the positive part, the next one is less than the current one. For all n, which means it starts from 1 or from 0. But you will see later on, our textbook also rephrase that, loosen the requirement. It doesn't have to be strictly decreasing. The positive part doesn't have to be strictly decreasing. As long as it is eventually decreasing, it's good enough. Okay. Second requirement is that the Bn convergent to 0. The positive part is convergent to 0. Okay. Now I remember my my professor actually dense this requirement to the following notation. The positive part should be eventually decreasing down to 0. Okay, so not only that it is decreasing, it is also convergent to 0. Okay, just the positive part, just the positive part. So you see that to prove, so to prove that an alternating series is convergent, you actually just need to show two things. The alternating series, this one I'm talking about, okay, where the Bn is the positive part. All you need to show is that positive part is convergent to 0 and decreasing. Okay. To be honest with you, this Bn is supposed to be the positive part. So if it is convergent to 0, as long as it is convergent to 0, you will see that it will, how to say it, it's kind of like most of the time it must be decreasing, right? Yeah, imagine if Bn, which is non-negative, right? Okay, now, so the minimum Bn can get is 0. Agree? The minimum Bn can get is 0. Okay, so for once you can show that the Bn convergent to 0, then most of the time it is actually decreasing, right? At least eventually, most of the time will be eventually decreasing. Okay, yeah. On the other hand, once you can show that the positive term is not convergent to 0, then it is not convergent. Okay, maybe I say another way. If the positive part is not convergent to 0, then the alternating series is divergent. Okay. I don't have any plan to actually show you the proof. You can see the proof. You can see the proof on page 752. Okay, but let me give you the intuition of the proof. Okay, why this will be true. Suppose, for example, I use the concrete example alternating harmonic series. Okay, alternating harmonic series, -1 to the n minus 1 of 1 over n from n equals to 1 to infinity. Okay, now we know harmonic series is divergent. We know harmonic series is divergent. Right? This is known. But notice that alternating harmonic series satisfy those two requirements. Okay, first, that the Bn, which is 1 over n, is decreasing. Proof. N is less than equal to n plus 1, therefore 1 over n is greater equal to 1 over n plus 1. So Bn is greater equal to 1 over Bn plus 1. Okay, and then second, Dn, which is 1 over n, is convergent to 0. This is almost not necessary to prove the limit n goes to infinity of 1 over n is 0. Okay, so by alternating series test, that's alternating series test, this alternating harmonic series is convergent. Okay, now the thing is, how do we actually feel it though? Okay, let's do the following. The sum that I need is actually 1 minus 1/2 plus 1/3 plus minus 1/4 plus 1/5 and on. Okay, now imagine on the number line, let's say this is my 0. Now, the first term is 1. So the first partial sum is 1. Okay, this is the first partial sum. Now, the second partial sum, 1 minus 1/2, I will subtract by something less than 1. Okay, so it becomes here now. This is 1/2, this is S2. Okay, so I start with 1, and this is 1 minus 1/2. This is 1 minus 1/2. Now next I will add 1/3. 1 minus 1/2 plus 1/3. Okay, so S3 will be 5 over 6. Okay, now then notice that for any terms after that, I will add the following. I subtract by something less than 1/3. I add by something more less than 1/4. I subtract by something less than 1/5, and so on and so forth. So notice that the, the sequence of the sum will be starting from 0 becomes 1, 0 becomes 1, and then becomes 1/2, becomes 5 over 6, and then becomes here. If you see the jump, it's basically jump from there, going here, going here, going here, going here, going here. You see? So eventually it will land somewhere here, right? And notice that the next sum always in between the last two sums. So for example, S3. Notice that S3 is between S2 and S1. You see that? Okay. And S4 must be between S3 and S2. S5 will be between S3 and S4. So Sn, the nth partial sum, okay, must be between S sub n minus 1 and S sub n minus 2. Okay, such that we can say the error must be of S sub n is less than a sub n plus 1. Okay, so you see that it's actually jumping this way. It's jumping this way, and then smaller and smaller and smaller and smaller and smaller and smaller. So the sum eventually get convergent into somewhere here, for example. Okay. Now that's the instinct of the proof. Now I will not prove that here. If you want, you can see the book for the proof, and I will see maybe on Wednesday I can prove that, show you a formal proof. But I believe our textbook actually give you a very good approach already. Okay, but to do proof, let's do the instinct first. Now, then I will do problem. I already did alternating harmonic series. Let's do another one problem. Let's say, for example, I do number 6. I do number 6. The series from 1 to infinity of -1 to the n minus 1 over natural log of n plus 4. Okay. Now, notice that this is a sub n. This is our a sub n. Okay. So can you tell what is the b sub n, the positive part? The positive part will be 1 over natural log of n plus 4. You see what I mean? Now, when you want to use alternating series test, all you need to show is this En is decreasing and the limit is 0. Okay, so the solution, actually the solution starts from here. Then, first part, En is decreasing. We can just use this notation here. So the proof, well, N is n plus 1 is greater equals to n. So n plus 1 plus 4 is greater equals to n plus 4. Therefore, 1 over n plus 1 plus 4 is less than equals to 1 over n plus 4. Therefore, b sub n plus 1 is less than equals to b sub n. Okay, in fact, this is for all n. Second, En is convergent to 0. Proof. I think this one is straightforward. No. This is equal to infinity. I'm sorry, not infinity. 1 over infinity, which is 0. Then, by alternating series test, this alternating series is convergent. That's for number 6. How about number 12? Number 12, the series from 1 to infinity or -1 to the n plus 1 of and e to the negative n. Is it convergent or divergent? Solution. Consider the Bn first. Let our Bn, the positive part, Bn e to the n. Okay, so I need to show that Bn is decreasing. Proof. Of course, n is less than or equal to n plus 1. So e to the n will be less than equals to e to the n plus 1. Right? Now the thing is both of them positive, such that n, I'm sorry. No, the thing is not. No, it's, if this is negative, then this is not true. This is not true. No, I can't do it that way. I'm sorry. So what do you think I need to do? Yeah, I try to show that n over e to the n is greater equals to n plus 1 over e to the n plus 1. That's what I need to show. This is what we need to show. That's what we need to show. The thing is, how do we show that? Let's see. So let me use another pen to give the sketch of the feeling. If this were true, then this have to be true. Right? If I divide both sides by n, e to the n, then I get n times e greater equals to n plus 1. But this is always true, huh? Don't you think so? This is always true because e is greater than 2. Right? Because e is greater than 2. E is greater than 2 such that for n positive, we get n times e is greater equals to n plus 1. Right? And then I can do it that way. Then e is greater than 2. So for n greater equals to 1, we get the situation n times e is greater equals to n plus 1. Then multiply both sides by e to the n. I get n times e to the n plus 1 greater equals to n plus 1 e to the n. And then n over e to the n is greater equals to n plus 1 over e to the n plus 1. I basically divide by e to the n, e to the n plus 1. But then I get b sub n is greater equals to b sub n plus 1. That's the end of the proof, or it is decreasing. Okay, but alternatingly, we're using color. Alternatingly, you can let fx equals to x e to the negative x. Notice that the continuous superposition function at n equals to b sub n. And then you do the derivative and show that the derivative is negative for some for some number greater than another number, positive number. So this is e to the negative x plus, actually becomes negative x times e to the negative x over, what am I doing? What am I doing? I don't need to do work that hard. this guy minus. So that's what I have earlier. I can factor e to the negative x out, and this is 1 minus x. Okay, and this is less than 0 for x greater or equals to 1. Less than or equal to 0 for x greater or equals to 1. You can start from 2 if you want. Okay. So fx is decreasing. And consequently, okay. Now second, I need to show that the Bn, the positive part conversion to 0. So positive part conversion to 0. I need to do limit n goes to infinity of n e to the negative n. This is equal to limit n goes to infinity of n over e to the n. How do we prove this? How do we show this is this? I know this is convergent to 0, but how do I do that? Repeat again.
No, I made a mistake.
You can use L'Hopital rule, actually.
The book continuous.
Yeah, right. But for us to do L'Hopital rule, I need to do continuous superposition function. So I let fx equals to x e to the negative x. Okay. Note that n equals to this bn. So actually, if you think about it, if since the beginning you use continuous superposition function, you don't need to do this, right? You don't need to do this part. You can just use this approach here right away, right? Okay. Well, anyway, I mean, there's no strict rule of how you do it. As long as you follow the test that we provided here, okay? And then what else? Limit n goes to x goes to infinity of fx equals to limit x goes to infinity of x over e to the x, and then you apply L'Hopital rule. This is equal to 0. So limit n goes to infinity of n e to the negative n also equals to 0. Then by 1 and 2, the series, oops, the series -1 and e to the negative n is convergent. Okay, number 16. Number 16. I try to find something that is not convergent, but I think I have hard time. Number 16 n equals to 1 to infinity of n cosine n pi over 2 to the n. Now notice that this is the alternating, right? Okay, so let E n be n over 2 to the n. So we need to show, I think you can easily show that, need to show that first Dn is decreasing, and second Dn converging to 0. I think that one is quite easy to show. When n equals to 1, when n equals to 1, this is negative 1. And then negative 1. For n, this is when n equals to 1, this is when n equals to 2, this is when n equals to 2. Okay? So by alternating series test, this series here is convergent. It's all convergent so far. I have 5 minutes left. Let's take a look on number 30. Number 30. Approximate the sum of the series correct to 4 decimal places. Approximate to 4 decimal places. For number 30, I have the summation from 1 to infinity of negative 1 to the n over 3 to the n and factorial. The solution, take a look of the dn. The dn is 1 over the positive term, the positive part. Okay, we need to find the k. Find k such that b k plus 1 is less than 0.0001. Okay, so this is 1 over 3 to the k plus 1 over k plus 1 factorial. Now from here you do trial and error. From here you do trial and error. Just do guessing. If I do the reciprocal, this is 3 to the k plus 1 of k plus 1 factorial has to be greater than 10,000. Right? If I do reciprocal. Okay, now then find the k such that the expression here is more than 10,000. So let's say I use k equals to 5. 3 to the 6 times 6 factorial. What's that? I need to get my calculator. So k to the 6 times 6 factorial. 6 factorial. I hope you know where to find factorial on your TI-30 or TI-36 if you happen to use TI-36. Ooh, so big. No. This is overkill. I just need 10,000. So let me change that to 3 to the 5th times 5 factorial.
Wait, really quick. There's a factorial button on our TI-30.
Should be.
Okay, keep going. I will figure it out.
It should be. If you look at the
I don't want to stop you in the middle of this. I just never saw that before.
Give me a second. I want to make sure that we have that too. So, are you at my browser right now? Do you see my browser now?
Yeah.
Okay, so TI-30 calculator. Let's see, which one do you use?
I have TI-30 X2S.
X2S, so something similar to this?
That pink one, it's identical to the pink one, so yeah.
Yes, yeah, something like this.
Yeah.
Okay, now then you can find it under, I wonder if I can enlarge this. Too small, I cannot see.
Oh, I'm sorry.
You press PRB first.
Okay.
Yeah, once you press PRB, then you will see exclamation, NPR, NCR. Is it right?
Nice, thanks, yeah.
Okay.
Yeah. Okay, there we go.
Go back to okay. So I tried 6 earlier. That's overkill. That's way too big. Way too big. Way more than 10,000. It's not necessary. When I try when k equals to 4, 3 to the 5th times 5 factorial. What did I get earlier? 29,160. This is equals to 29,160. Now you can try when k equals to 3, but at least I know that if I use k up to the 4th term, when I add up to the 4th term, my sum is good enough. Okay, so I will do the following. What is the first term? Let me copy this down. Sorry, I'm a bit over time. So copy this and then put it here. That is equal to, that's equals to negative 1 over, when n equals to 1, that's 3, plus 1 over 9 times 2, minus 1 over 27 times 3 factorial is 6, plus 1 over 81 times 4 times 24. So if we add these, the sum that we get is actually accurate to 4 decimal places. 1 over, this is 2 or 162. And then plus 1 over, I don't know what is this, very big number. So if you add these 4 numbers here, this number, the error will be less than 0.0001 from the actual sum. If you add them up to infinity, sorry, it should be only up to 4 here. Okay, suggested homework 11.5, number 3 to number 19, and then number 23 to number 29. Now, if you have a chance, try to take a look on this number 32 up to 34. It's not necessary for this, but we will see that again in, I think, at 11.7. for 11.8. Yeah, we'll see that again in 11.8. Okay then, see you Wednesday.
Can you show me the 11.4 homework? I didn't write it down.